Yes, sir.
Okay. Consider a particle subjected to a particle subjected to a particle subjected to two different harmonic motions or SHM. Let us consider x1 is equal to a sine a sine a sine omega 1 t. Second one, x2 is equal to b. Amplitude is different, okay, for both sine omega 2 t. But in the addition of two waves, we had omega 1 and omega 2 is same, right? Omega t and omega t, but amplitude will be different. But here it is, the frequency is also different. So the resultant motion is given by the resultant motion is given by x is equal to x1 plus x2 is equal to a sine omega 1t plus b sine omega 2t. This is the resultant. Okay, so the graph, I will give you the video. I'll show you the video in the next class, please. For time being, you just copy this, the Weed phenomenon. Okay, this is the displacement. The phenomenon is like this. Please copy this. Copy this. Here, actually, the new wave for x is like this. Okay. The curve will be like this. Again, the amplitude goes on increasing in the loop by loop. Goes to 0 again, then gradually increases. See the amplitude. This is what the resultant wave, okay, the black colored line. Again, it reduces to 0, then again it increases maximum, and again the amplitude will be reduced and becomes 0. Again increases maximum, then it goes down. This is what the resultant, the dark line or the dark curve indicates it is a resultant of x. Okay, so this is what the beat principle, and each loop is called as a beat, single beat. The sound will be like this. Maybe if you have a instrument, so if you have two SHM, if you play the instrument with the two SHM of different frequency, omega 1 and omega 2, then sound will be initially it will be maximum and goes down, increase the maximum, down, maximum, minimum, maximum, like that. It will give you a loop, right? So the sound may be like this, wow, 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 like that. That sound, that type of sound is coming out from the musical instrument, right? Maybe the sound may be whatever, but the sound will be having a minimum and the maximum amplitude. Okay, so that's what the beat principle that we will discuss, or we'll see the video, we'll come to know what is beat principle. Okay. So actually, this curve is the black curve is a resultant. But what about x1 and x2? See here, if you have a curve, let us take, I'll take two curves, okay, x1 and x2. This is for x1, this is x2. I don't think it is a waste of time to spend more time on this one, because it is not there in the syllabus, okay, beat. But he may ask you the definition, okay. Okay, so I'm going to explain this, why, how do you take x1 and x2 and how do you add this one, okay. I'll take another 2 minutes for this. Okay, the first curve, let us consider the curve x1 is like this. X1 curve is like this. It is SHM, okay, no doubt it is SHM, and this is what your time for the first loop or one cycle. Okay, the second curve I'm going to take here. So the curve, the t is somewhat different. If the t is different, then automatically frequency will be different, right? It is not same. I'm going to take the curve like this. The curve will be having little bit smaller frequency. See, this t is different. Okay, this is t1, this is t2. T1, T2 is not same, but addition of two SHM T1 and T2 is same. But here it is different, T1, T2. That's why omega 1 here, omega 1, omega 2. You know what is T, and the relationship between T and omega, both are same, right? It is correlated. So depending on omega 2, T. So if you add these two vectors, or these two SHM, what happens? So let us combine this one. I have a video, I'll show you in the next class, okay? So if you combine this, what happens? Say this is the frequency somewhat less, right? For the completion of one cycle, it has to reach here, but instead of very small frequency, maybe having like this, see the curve. So it will end up with this point somewhere here, right? And it will be end up with this point. So it goes on reducing, right? So like this. So the curve is not exactly matching this first curve. Forget about amplitude. Amplitude may be larger or smaller, but the frequency is different. That's why it is not merging with a point to point, right? This point with this point, this point with this point. So this gap is gradually increasing. Look at this. So as a result, see here the resultant will be like this. I can show you the resultant of these two waves. So the resultant will be, see the curve. Initially, it will be increase, okay, increases, still increases, then it goes down, slowly goes down to 0, then again it increases, okay, maximum loop, then again it goes down, 0, then it increases, right? Sorry, yeah, increases to maximum loop, and it will come. So here you can see the loop. So this is what the loop I said. See, can you see this? This is the loop, right? This is the loop. What I have drawn here, that we will get, right? This type of wave can be generated by adding two different SHM with a small difference in the frequency. We'll get a loop. Is it okay? See, once it reaches to this point, it is 0. Again, it will be 0 here, but in the between, it is maximum. The green curve indicates it is a resultant. Is it okay? So like that, we'll get a big phenomenon. Is it okay? Any doubt? Hello, am I audible?
Yes, sir.
Okay, are you clear? One thing you should remember, beat principle exists only when there is a difference in the frequency. But superposition exists only when the frequency are same, but amplitude will be different. Okay, but beat phenomenon, both amplitude as well as frequency will be different. If you merge two SHM, then we'll get a beat phenomenon. Shall we go to the next slide? Next concept. Okay, it's almost 10:35. We spent 20 minutes. Okay, finished. Hello. Okay, next is write down vibration analysis. This is what very, very important concepts. Vibration. Is the screen is visible? Vibration analysis. Vibration analysis. Okay, you know the spring mass system that we have discussed in the beginning. So all the vibrating body can be shown in the form of spring mass system. There will be a stiffness element, there will be inertial element or the mass stiffness element or resisting element. This called as a spring, right? So here vibration analysis, there are three methods of vibration analysis. Vibration analysis is nothing but to find out the natural frequency. Different types of analysis are there. How do you find out the natural frequency for a given system or a vibrating system? Is called as vibration analysis. Analysis or the method of finding a natural frequency for a vibrating system is called as vibration analysis. Okay, there are three different methods. One is the first one is equilibrium method. Please write down equilibrium method. Equilibrium method, or it is also called as D'Alembert's principle. D'Alembert's principle. First one. Second one is called as energy method. Second one is called as energy method. Energy method. The third one is called as Rayleigh's method. Rayleigh's method. These three methods are very, very important. At least two methods will be asked in the exam. Method. Rayleigh's method. Three different vibration analysis methods are there. The first one is equilibrium method, or it is called as a D'Alembert's principle. Second one is energy method. Third one is Rayleigh's method. Copied? Okay, let us go to the next slide. The first one. What? Equilibrium method. Write down. Equilibrium method, or it is called as D'Alembert's principle. D'Alembert's principle. Equilibrium method, or it is called as D'Alembert's principle. Okay, note down below this. Note down. It is based on the principle. It is based on the principle. It is based on the principle that. It is based on the principle that whenever a vibrating body, whenever a vibrating system is in equilibrium, whenever a vibrating system is in equilibrium, the algebraic sum of the forces, the vibrating body is in equilibrium, comma, the algebraic sum of the forces and moments The algebraic sum of the forces and the moment acting on it is zero. Acting on it is zero. I repeat, it is based on the principle that whenever a vibrating system is in equilibrium, the algebraic sum of the forces and the moment acting on it is zero. Full stop. This is in accordance with D'Alembert's principle. This is in accordance with D'Alembert's principle that D'Alembert's principle that D'Alembert's principle that the sum of the inertial forces, the sum of the inertial forces, sum of the inertial forces and the external forces on the body is in equilibrium, on the body in equilibrium, on the body in equilibrium, in equilibrium, must be zero, must be zero. Copy this figure. I'll explain what is the meaning of the above sentence. Copy this, please. M. We have the reference line. We will take it as this is what my reference line. The mass is in the equilibrium position. Let us take mass is reached somewhere here. Okay, let us erase this. Okay, just a spring. Okay, it is just a spring. There is no mass here. If you add a mass, then it goes down a little bit down compared to the previous place or position. Is the screen visible? Hello?
Yes, sir.
Okay. This is what delta. The mass is displaced to a distance delta. If you put a mass, okay, if there is a spring, it will be somewhere here. But if you put some mass, then it goes down and it will reach to delta distance. It will travel a distance delta. The spring constant is K, okay? K. Now, if you move further, I have to finish this. Please do it fast. You need to keep some distance, okay? So I will take a spring. Okay, this is a spring, and you are going to apply a pulling force. Okay, if you apply some force, the spring, if you pull it down, so you have applied a external force, then it will reach to somewhere here. Okay, this is what the position after the application of the load. For any vibrating body, you know that for any vibrating body, you need to apply the force in the first cycle for the pre-vibration. Then it starts to vibrate its own, right? It continue its vibration. So the total displacement, let us consider, this is the total displacement. The total displacement is delta plus x. This is what x. This is x plus delta. Copied? I have another analysis. Let us take, this is the mass at this position. Which position? At delta position. Yeah. I have to, okay, we'll do it later. Here also I have mass at this position. Copied? This is K. Hello, copied? Very, very important. This will be asked in the exam. Okay, copied? I need to have enough space in this region, okay, after the third figure. Hello, copied?
Yes, sir.
Okay, let us proceed. Okay. See, this is the first figure. I have a spring, I have a spring. I have not loaded anything, okay, on the spring. Then the position is somewhat like this, because the load applied on the spring is 0, and it is hanged to the floor or a hook, and I have not applied any load on this, just it is free. What I'm going to do is I'm going to add a mass m to the spring, and I'll hang it at the other end of the spring. This end, other end is this one. One end is connected to the hook, and the other end is free. At the free end, I'm going to apply the load M. Due to the self mass or the mass applied, it will be deflected because there is extension in the spring or the expansion of the spring because of this mass. The expansion is called as delta. The displacement is called as delta. Is there any doubt in this? Delta. Is it okay? Hello?
No doubt, sir.
No doubt. Okay. Next, see here, what I'm going to do is just a minute. I'll erase it, okay? I'll show it here. You keep it as it is, no problem, but I'll copy this somewhere here. Okay, so this is what the distance traveled after the application of the external load. Okay, this is what X. The total distance traveled by the mass is X plus delta. X plus delta. Okay, now see, after the application of after loading M or the mass or the spring, it will be deflected from this position to this position. It reached to this position. Now the displacement is X. Displacement is X. If you analyze the force, see, this is what my mass. It is somewhere here, reached here. I'm going to just copy of this one. This is my mass, and see, you're going to apply the load on the spring, means the application of load will be in the downward direction. The first force is, this is what M into G, mass into acceleration due to gravity. That is the force, or it is called as W, right? That is capital W. A small w. Okay, let us take W. W is a weight of this mass. Weight or the force acting in the downward direction. This force in the equilibrium condition, because this is the equilibrium method. In the equilibrium condition, let us assume it is an equilibrium condition. In equilibrium condition, this force is balanced by an opposite force. It is in the upward direction. Upward direction. So this force is balanced by an upward direction. What is that force? That force is the resistance force offered by the spring to a deflection of delta. That force or the resistance force by the spring is called as K into delta. K into delta. What is K? K is the spring stiffness. Delta is the displacement. So this is the resistance force offered by the spring to displace at a distance of delta. That is in the upward direction. So if you pull it down, if you apply the mass, what happens? The mass will move down, but the resistance force will be in the upward direction. So this is the resistance force, this is the weight. So any doubt in this analysis of force in the second figure? There are two forces. One is spring force, that is K into delta. Second one is mg, that is a weight of the body. Is there any doubt? There are two forces in the second figure. Any doubt? Don't hesitate. I can explain it once again if you have any doubt. Hello?
No, sir.
No. Let us go to the next third figure. Third figure, what I'm going to do, I am going to apply the external force, okay? Here there is no external force. It is due to the self mass. That's why we'll have two forces. One is mg and another one is K delta. self mass or the self weight. But here in the third figure, what I'm going to do is I'm going to apply a load of F, applied force F, applied force F. Is it okay? So if you apply the force in the downward direction, it is a free vibration. Okay, you know what is free vibration? Free vibration, first cycle I'm going to apply the load and I'll leave it, so it starts to vibrate, up and down motion, right? So there is no further force acting in the second cycle, third cycle. Only during the first cycle I'm going to apply the load. Here also I'm going to do the same thing. I'm applied a load of F on the mass. I pull it down and I leave it. Is it okay? So if you pull it down, at what distance you're going to pull? I'm going to pull it for a distance of x, for a distance of x. So that is the distance traveled. The initial position is this one. Which one? This one, because of the self weight. Actual position is this one, but due to the self mass, it is moved to a distance of delta. That's why it is right now here. But from this distance, I have traveled a further distance of x due to the external force. So it is reached to somewhere here, and the distance traveled from the initial position to the final position is x, and the total distance from the initial force, total distance by the application of load as well as the self mass is called as x plus delta. Is there any doubt? Is there any doubt? Hello?
Yes, sir.
Any doubt?
No, sir.
No, clear. Okay.
Sir.
Yeah. Okay, let us proceed. The next one is I have to analyze the force in this position, okay? Because I have added a new force, that is F. In equilibrium condition, I need to consider all the forces. Summation of all the forces and the moment is equal to 0 in an equilibrium condition or equilibrium state. That is the statement called equilibrium method or D'Alembert's principle. What it says, D'Alembert principle, it says that the first sentence you read, it is based on the principle of that whenever a vibrating system is in equilibrium, if it is in equilibrium, let us consider the third position is also in equilibrium position. In equilibrium, algebraic sum of the forces and the moment acting on it is 0. We have taken the force in the second position. We have only two forces, that is K delta and mg, that is two forces. One is upward and the one is downward. So it is in equilibrium position. I have to analyze the forces in the third position also. Third position is not similar to the second position because we have applied an external force. So I'm going to analyze the force in this figure, okay, for the third position. So here I'll take a mass, a representation of mass, okay. So this is my mass, m. The first force, the very first force is always mg. You know that. That is self mass or self weight. It is in the downward. Downward. Any doubt in this? Same thing what we have copied from the previous figure or the previous second one. The second one, spring force. If you pull it further, what happens? Spring force will be increased, right? It is not same as the K delta because the distance traveled is x plus delta, not delta only. It is traveled to a distance of x plus delta. X is added. So spring force also increases, right? As the distance traveled increases, automatically spring force also increases. The spring force, the direction of the spring force is upward. What is the value or the magnitude of spring force? Can anyone tell? What is the magnitude of a spring force acting in the third position? Please, can anyone tell me? Spring force, distance traveled into spring constant. Now, what is the distance traveled for the third position? Total distance traveled. Can anyone please open your mouth? Otherwise, it will be difficult to proceed for me. Can anyone answer?
X.
Yes.
X distance X.
Not only X, the total distance
X
traveled by the
plus
spring
sigma.
mass is what?
X plus
X
delta.
plus delta. Please remember X plus delta. Delta is also there. It is already travel distance, right? You cannot leave delta. X plus delta. K into this force is K into X plus delta. This is what the spring force in the upward direction when it is reached to the maximum extent, that is X plus delta distance. K into X plus delta. Is it okay? This is what the spring force. Next, what else is there? Look at this. In the equilibrium position, look at this. I am going to pull it to the extreme end and I will leave it because it is a free vibration, right? I will leave it. What happens if you leave it to the extreme position? If you leave it, it starts to move in the upward direction, right? Because of the spring force. It starts to move in the upward direction. So while moving in the upward direction, there will be acceleration. There will be acceleration. You know what is displacement, velocity, and acceleration? Displacement is the distance traveled by the body. Velocity is a rate of change of displacement. Acceleration, it is a rate of change of velocity. The mass will be moving with the acceleration. It is not moving with constant velocity. Constant velocity means velocity will be same here, 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 everywhere it will be same. But it is not like that because the mass will be moving with a slower rate at the end position and it will be maximum. The velocity will be maximum at this middle position or the equilibrium position. Again, it moves up. The velocity will be goes on decreasing. It will become zero at the extreme position. Again, velocity coming down. It is increasing. It will be maximum at the equilibrium position. Again, it will moves down and it will be minimum at this position. Again, it moves up. Velocity will be so velocity is continuously varying. Velocity is continuously varying. If the variation in the velocity is called as acceleration, right? Acceleration. If the body is having its own mass and if there is acceleration, then there will be what? Inertial force. Inertial force. If you are moving in a bus, if the brake is applied suddenly, you are having a mass and if you apply the brake, what happens? There is a variation in the velocity. There is an acceleration. Due to that acceleration and the mass of your body, you will move in the forward direction, right? The same concept will be applied here. So because of the acceleration, the body will have its own inertial force. That inertial force will be in the direction of motion of the body. What is the direction of motion of the body? It is upward right now. We are going to take at that instant. At that instant, the body is trying to move in the upward direction. That's why inertial force is also in the upward direction. Which direction? Upward direction. So I'm going to mention another force that is called as inertial force. Inertial force. What is the magnitude of inertial force? That is m into a. What is a? A is acceleration of the mass. M into a. This term is called as inertial force. Inertial force. Inertial force. This is called as spring force. What is this? K into X plus delta. Spring force. Please write down. If possible, you can write it here. Spring force. This is what? Self-weight. Self-weight. How many forces are there in the third position? There are three different forces. One is spring force, second one is self-weight, third one is inertial force. You know what is inertial force? Inertial force is due to the acceleration of the body. Once you pull it and leave it, what happens? Its body starts to move in the upward direction. Moving with acceleration. Moving with acceleration is nothing but there is an inertial force. That inertial force is equal to ma. Which direction? It is in the upward direction. That's all analysis of force is for. Copied? How many forces are there in the third position? Three forces. One is self-weight, second one is spring force, third one is inertial force. Here there is no matter of inertial force in the second position. Why? Because We have applied load and we have left. We left. There is no vibration here in this case, second position, right? But third position, there is a vibration, correct? That's why there is an extra force that is called as inertial force. I hope you copied. All of you copied? Is it possible to take this F? Can anyone answer? No, you cannot take F because we are not going to consider the equilibrium condition when you apply the load. You just apply the load and leave it. We are going to release that load F. Then we'll see the vibration. Correct? So you cannot consider this F in this equation. Okay? All of you finished? Copied the figure? Yes. Write down below. Forces acting on the mass. Forces acting on the mass. The first force, weight, or it is self-weight. Is equal to mg. Direction downward. Please write down downward. Second one, spring force. Spring force is equal to k into delta or x in x delta x plus delta. What direction it is? Upward. What is the third force? Third force, inertial force. Inertial force. It is equal to ma, upward. Time up. Do it fast. Do it fast. I have to complete this derivation. Copied? Hello? Am I audible?
Yes, sir. Yes,
Okay.
sir.
Copied?
Yes.
Okay. Next. According to the D'Alembert's principle, write down. According to D'Alembert's principle, what it says, summation of all the forces must be equal to 0 in equilibrium condition. In equilibrium condition, summation of all the forces must be equal to 0. Also, forces and couples must be equal to 0 in equilibrium condition. Let us consider the third position is in equilibrium condition. Equilibrium condition. Summation of all the forces must be equal to 0. What are the forces? Inertial force, spring force, and self-weight. Sum of all the forces. Write down. According to the D'Alembert principle, summation of inertial force plus external force must be equal to 0. This is what the D'Alembert's principle. Okay. Now, where is the inertial force? Inertial force, what is the maximum? What is the value of inertial force in this equation? This is m into a. Upward or downward? Upward, positive. M into a. Next, external force. External force means self-weight and spring force. Spring force is upward, that is k plus k into x plus delta. Next, downward, mg minus m into g is equal to 0. Only three forces. is equal to 0. You simplify this equation, m into a plus k x plus k delta minus mg is equal to 0. Is equal to 0. Look at this, the figure. Here in the second position, look at this. mg is equal to, in the second position, what is the condition for the second position? There is no external force. Only two forces are there. K into delta is equal to mg in the equilibrium position. So second position, K delta is equal to mg. Write down. Second position, K into delta is equal to mg for second position. This is satisfied only for second position. So substitute this. M into A, K delta, mg, both are equal. These two terms will be get cancelled, right? According to the second equation. Plus kx is equal to 0. Understood? Second position. Why I'm going to take k delta is equal to mg? Because second position, only two forces are there. Summation of all the forces must be equal to 0. Means k delta minus mg is equal to 0. Therefore, k delta is equal to mg. Okay? Therefore, these two terms will get cancelled, minus positive. So that's why. So this is what the equation. I'm going to rewrite this equation again. A is equal to k by m, sorry, a plus k by m is equal to 0. This is what my first equation, equation number 1. Any doubt in this equation? Very simple, right? Okay, next line. For SHM, what is the displacement equation for SHM? Please go to the previous slide derivation before the problem what I've solved. Derivation, first derivation. What is the equation, displacement equation, general equation? Please, can anyone tell? Do it fast. Turn the page and tell me the equation for SHM. Is it correct? This equation we have derived, right? That is a plus omega square x. Here we are going to take omega n because it is the natural frequency for natural frequency. Is it okay? Okay. So this is the equation what we have derived in the previous derivation. A plus omega n square x is equal to 0 for SHM. So equating equation number 1 and 2. Equating equation 1 and 2. Are you copying or not?
Yes, sir.
Okay. Equating equation number 1 and 2. I'm going to equate it. A plus k by m into x. Oh, x miss agida. Please look at this. K by m into x. Okay. K m into x is equal to, what is the next equation? A plus omega n square x. Here everything is same, but this one. Therefore, omega n square is equal to k by m. Therefore, omega n is equal to square root of k by m. What is this? Natural angular velocity is equal to square root of k by m. Natural angular velocity is equal to square root of K by M. This is what the equation says. The first equation, okay? Omega N equation for a spring mass system. Next, therefore, natural frequency is equal to f of n, that is natural frequency. What is frequency? Frequency equation omega n by 2 pi, right? That is, I have given in the note. Omega n by 2 pi is nothing but frequency or natural frequency, right? It is equal to Fn is equal to, what will be the equation, final equation? Omega n is 1 by 2 pi. Omega n is nothing but K by M. This is what the natural frequency equation. Equation number 3. This is equation number 4. Or you can write this equation, Fn is equal to 1 by 2 pi square root of G by delta. Why? Because mg is equal to K delta, right? K by M is equal to G by delta for the second position. Next is the last one, time period. T P or the time period is equal to 1 by Fn is equal to 2 pi square root of M by K. It is a reciprocal of Fn. Equation number 5. That's all. Very simple. First equation, you should know how to derive the first equation. Second equation, directly you copy from the first derivation. You just remember it and copy it. Compare those two. We'll get a term for omega n, that is K by M. So omega n square is equal to K by M. Omega n is equal to square root of K by M. Then Fn, omega n by 2 pi. You know the equation for Fn. Fn is equal to omega n by 2 pi, that I have given in the note. Because frequency is number of cycles per second, right? So omega n is angular velocity, radians per second. 1 second, how many radians it rotates? For 1 cycle, 2 pi radians. That's why omega n by 1 cycle, that will gives you number of cycles per second. That is omega n by 2 pi. Is it okay? Any doubt? Hello? Hello? Am I audible?
Yes, sir.
Clear?
Yes, sir.
Any doubt?
No, sir.
Hello?
No, sir.
No doubt. Okay. I'll explain it once again for 2 minutes. Please look at the slide. First one, there is no mass. First figure, there is no mass, only spring is there, so there is no displacement. Second figure, I'm going to apply the mass. Due to the self weight, there will be deflection in the spring. Spring will be expanded and the mass will be traveled to a distance of delta. This position, if you analyze the forces, and this position, second position, there will be a force, the downward force, that is mg, self weight, and this self weight is balanced by another force that is called as a spring force. The spring force is equal to K into delta, the deflection, delta into K, spring stiffness. That is the force. This is the second position analysis. Third position, I'm going to apply the load in the downward direction and I'll leave it. So due to that load, the mass will be displaced to a distance of x from the initial position. Initial position means delta position. So the total distance traveled by the mass is x plus delta that I have mentioned. Now I have to analyze the forces acting on this mass at the equilibrium position, because this principle is equilibrium method, right? Equilibrium position. And in equilibrium position, or if the system is in equilibrium, let us assume or let us consider all the forces acting on the mass. The first force is a self weight, that is downward direction, m into g. Second force is a spring force, that is in the upward direction, because the resistance for the spring for the deflection, that is k into total distance traveled, that is k into x plus delta, that is upward. Then the third force, if you apply the force in the downward direction, if you leave it, what happens? The body will starts to, or it tries to move in the upward direction with acceleration. If there is an acceleration, then there will be inertial force. The inertial force is nothing but m into a, mass of the body into a. That is also in the upward direction, because the body is trying to move in the upward. So that is inertial force. So there are three different forces. One is self weight, that is downward. Second one is spring force, upward. Third one is inertial force, upward. Three different forces are acting on the system for the third position. Now, if you take equilibrium position, or principle of D'Alembert's principle, it says that summation of all the forces acting on an equilibrium system is equal to 0. What are the forces acting on this equilibrium position? Three forces. You take all these three forces. Two are positive because upward, one is negative, that I have taken here. According to the D'Alembert's principle, inertial force, sum of inertial force and external force is equal to 0. Inertial force is ma, external force is these two forces. One is mg and k into x plus delta. So ma is positive because it is upward. K into x plus delta is upward. That's why it is positive. Mg is negative because it is downward. That is the equation or force equation. Next, ma into, if you expand x delta kx plus delta x, k delta minus mg is equal to 0. Here in the second position we have only two forces. One is k into delta and mg. One is upward, another one is downward. That's why k into delta is equal to mg. K into delta is equal to mg. If you substitute it, these two terms will be cancelled and we'll have equation ma plus kx is equal to 0. If you rewrite the equation m, or if you divide the equation by m, entire equation by m, we'll get a plus k by m into x. M cancelled, a, and here k by m is equal to x is equal to 0. So if you please rewrite the equation, don't get confused here. I can rewrite this equation. See, this is k by m into x, okay, is equal to 0. That is the first equation. From SHM, if you go to the previous derivation, we'll have an equation. We have derived equation for SHM, that is a plus omega square into x is equal to 0. We are going to take natural frequency. That's why natural angular velocity n, omega n square is equal to into x is equal to 0. That is equation number 2. If you compare these two equations, equating equation number 1 and 2, we'll have an equation like this. All the terms are similar, but here omega n is there, km is there. These two terms are equal. That is omega n square is equal to k by m. Therefore, omega n is equal to square root of k by m. That is equation number 3. Next, if you want to derive the equation for Fn is equal to, that is natural frequency is equal to omega n by 2 pi. That you know, I have given a note. So if you substitute omega n value, it is square root of k by m. So if Fn is equal to 1 by 2 pi, if you substitute this k by m, if you take the value of k by m from the equation number 2 or the position 2, that is mg is equal to k delta, k by m is equal to g by delta. So that you substitute, will have a Fn equation in terms of g and delta. Time period is equal to 1 by Fn, it is equal to 2 pi. 1 by Fn is a reciprocal of Fn equation. It is 2 pi into square root of m by k. That is the fifth equation. Is it okay? Hello?
Yes, sir.
Thank you. Just a minute. I'll save it. D'Alembert's. Okay. Oh, now it is almost 40. What is the third hour? It's almost 11:20, right? Okay, thank you. Leave it. No problem.